this particular presentation is all about solving some more ODEs with the Laplace transform method. And in particular, we'll have a look at an ODE involving a discontinuous right-hand side. Now, I've also got an example where hopefully I can convince you, again, that the Laplace transform method has certain advantages over, say, the method of undetermined coefficients. So just to remind everyone, Laplace transform is an integral transform. You take a function of t, multiply it through by this exponential, and form this improper integral, which is actually a function of s. This is the table that we've been working with in classes. Essentially, a table is useful for quickly computing transforms, but really, the real gold there is when you want to calculate an inverse transform. That's why it's really necessary, at least within the context of these presentations. Okay, well, we've already looked at this, but again, just to refresh your memory, transform of derivatives. Okay, using integration by parts, you can come up with the following transform of derivatives, and we've discussed a proof that I've just, I won't talk about that now. And from an ODE point of view, think of f here, or f prime, as the solution and its derivative of some differential equation that we want to calculate the solution to. Okay, well, for initial value problems, the idea of Laplace transforms is transform both sides of the original problem, incorporate the initial conditions, solve the algebraic problem for, say, big Y of s, and then untransform everything. Now, one of the advantages of the Laplace method is that it incorporates the initial conditions all into the process. Now, this is best illustrated through an example. So here's an initial value problem, IVP, first order linear. Now, yes, you could solve this using the linear method, but I want to show you how you can use the Laplace transform methods to solve this problem. Okay, so the right-hand side here is the Heaviside step function. So if I was to draw that, the graph would look something like this. Oh, sorry. 1. So it's essentially 0 until I hit the point t equals 1. Then it gets switched on. And after, to the right of t equals 1, the u of t minus 1 is just 1. And in the context of these classes, we define the value at the jump point to be 1/2. Now, again, depending on how you define the function at the jump point, it's not a big deal. Okay, you may not even define it at t equals 1. Okay, it doesn't change the transform at all. Okay, so this right-hand side is now a Heaviside step function. Okay, well, to solve this, we're going to apply the technique that we've seen in the previous lecture. So let's take the transform of both sides. And then use the linearity of the Laplace transform on the left-hand side and compute the transform of the right-hand side. Okay, so what's the transform of the Heaviside step function? Well, if we go to our table, equals 1, I look across, I find the transform. So for our case, the transform of the right-hand side is going to be e to the minus s all over s. So here on the right-hand side, I've used a table. And on the left-hand side, I've used the linearity of the Laplace transform operator. Okay, well, on the left-hand side, I can keep going and just look at the transform of derivatives. So L of y prime is going to be s times big Y of s minus y of 0. And I know what y of 0 is, it's just 0. So using the transform of derivatives, and just to simplify, let's just introduce my big Y of s notation. We obtain the following. All right, so on the left-hand side, I'm going to get something like s big Y of s minus little y of 0. Now this is just big Y of s. And I get something like this. Now little y of 0 is the initial condition and it's 0. So I can, that term there is just going to be 0. Okay? So the initial condition yields the following. Well, that middle term 0, and I can take a common factor of big Y of s and then make it the subject. Okay? So now what I would like to do, I've solved the algebraic problem. Okay, so I've solved the transformed problem in the transform setting. What I would like to do is now untransform everything and recover little y of t. Okay, so can I get back to my ODE environment just by taking the inverse transform of this? So again, we're faced with a dilemma here. What's the best way to calculate the inverse transform of this? Well, if you look closely, it's this product. Now, if I look down the right-hand side, an exponential times a function of s. An exponential times a function of s. Okay? So if I look down here, it looks like the second shifting theorem would be suitable. Okay? So remember we looked we spent at least one lecture on the second shifting theorem. In particular, let's just make this big G of s. The second shifting theorem from our table says that to compute the inverse transform of this form, what I do is I calculate the inverse transform of big G and then shift it and multiply through by this Heaviside step function. So the thing that's driving our solution now is this. I want to take the inverse transform of this. Okay? So we apply the second shifting theorem. Okay. With, well, from our table, C is going to be 1 and big G of S is 1 on this. Okay? So really what's driving the solution method now is let's calculate the inverse transform of big G. Then shift it and multiply through by an appropriate Heaviside function. Okay, well, how do we calculate the inverse transform of this? Well, you could use partial fractions. Break it up. Is it necessary? No. Can anyone suggest what we to the numerator? Right, just add s and take s away. Of course, if you want to use partial fractions, you can. So if I now break that up into 2 bits and cancel, I'll get this. Okay? Now this method won't always work because it's hard to see sometimes what to do with the numerator, but it works in a lot of simple cases. Okay? A lot of simple cases. Now what do I want that form and not, say, the original form? Well, the original form doesn't really pop out in the right-hand side of this table, but these two forms are not going to be too bad. Okay, so let's calculate this, the inverse transform here. Okay, so the inverse transform of 1 on s, if we look at our table, is just 1. And how do we take the inverse transform of 1 on s plus 1? Well, it's going to be something like an exponential, right? So okay, so we've calculated the inverse transform of big G of s. What we want to do now is appropriately shift it. By the second shifting theorem, the inverse transform of this is just, okay, if I look it up on my table, the second shifting theorem's there. Oops. It's this product. Okay, so I've just calculated little g of t, it's here, so I want to multiply and shift appropriately. Okay, so I replace t with t minus 1 in brackets in here. Okay? So hopefully you can see that it's all gone back to recognizing that I had a function of s times an exponential. Okay? This means that, provided I can calculate the inverse transform of this, I can use this second shifting theorem. That's the idea. Okay, so what have we calculated here? Well, let's break it up into 2 bits and see actually what's going on here. Well, for t to the left of 1, what's this going to be? 0. So 0 times that, everything will be 0. Right? And for t greater than 1, this will be 1, so it'll be 1 times all of this. Now, it turns out that at t equals 1, this is going to be a half, according to our definition, and I'll get 1 minus 1 in here. So actually I get 0, so I can define it as this function for all values of t. Okay? Questions? Okay, that's not an easy example, but we would expect you to be comfortable with a question like that because it really tests a lot of the basics of Laplace transforms. Okay? It tests transform of derivatives. It tests second shifting theorem. It tests applying the initial conditions. It tests using the table. Okay?
I think that equal sign goes zero.
These two parts connect up. Okay? So the two parts of the solution actually connect up as a continuous solution, even though the right-hand side of this is discontinuous. Okay? So this is quite common actually in differential equations. You may have a discontinuous forcing function or something on the right-hand side, but you've still got a continuous movement. Okay? Okay, here is a second order problem. And we are asked to solve it. And you'll see the right-hand side is kind of defined in a piecewise manner. So how do we solve it? Well, the idea, of course, is to use Laplace transforms in this context. And the idea is to take transforms of both sides of the original dE and then use transform of derivatives, incorporate the initial conditions, solve the algebraic problem, and then untransform everything. Now for this particular example, let's just have a look at this Q function. So essentially the Q function increases at this sort of linear rate, if you like. And then what happens is the function just flattens out. So you can think of this function as, you know, like a ramp loading type situation. Okay, so let's see if we can solve this problem. So we take the Laplace transform of both sides. Okay, now how do I actually take the Laplace transform of little q? Well, what I would like to do is simplify it. Maybe I can write q in terms of a Heaviside step function. Okay, so in terms of our Heaviside step function, how can I write the function q? Well, you can see initially the function t is happening, and then what happens is the function t gets switched off and I just get this constant value. So let's just play around and see if I can come up with it. Well, initially I've got t, and then the t has to get switched off, and then pi on 2 has to get turned on. So everything happens at pi on 2. So with those two terms, t's on and then t gets switched off. But I haven't quite covered all the bases yet. What I would like after the to the right-hand side of my of this sort of point here, I would like just pi on 2 to remain. So what I can do is just take my Heaviside step function and multiply it through by pi on 2 to get the proper height. Okay? Okay, well, actually that form is going to be pretty nice. You can see that I've got a common factor here of this Heaviside step function, and if I factor them in the right way, I can end up with a t minus pi on 2. That form there. Second shifting theorem. Okay? So, let's take the Laplace transform of both sides of, say, star. Now, the Laplace transform is a linear operator, so I won't write down all the steps here. Okay? Now, using transform of derivatives, I can come up with the following. So it's going to be okay, that minus that. Okay, so by transform of derivatives, this is just this. Now, big L of y, that's just, in the S notation, is just this. And what about this? Well, let's simplify up here, take the common factor. You're going to get something like this. Okay, notice I've got a t minus pi on 2 and a t minus pi on 2. That's necessary for the second shifting theorem. All right, well, let's see if we can simplify this. Well, y of 0 is 0, y prime of 0 is also 0. So that's going to be 0, that's going to be 0. I've got a common factor of big Y of S. Now, what's the Laplace transform of little t? Well, it's just 1 on S squared. And what's the Laplace transform of this product here? Well, by the second shifting theorem, it's this exponential times the transform of this sort of unshifted function here. Okay, so if you just cover that up, you'll get t. So essentially, I just want to take the Laplace transform of t here and then multiply through by e to the minus pi on 2. Okay, so it's a second shifting theorem. Okay. So second shifting theorem and table. Okay, so let's solve for the big Y of S. Okay, I've got a common factor of 1 on S squared here, and if I bring that down, I can form something like the following. Okay, so we're almost there. We've now solved the transform problem. To recover the solution to the original IVP, we want to take the inverse transform of both sides. Okay, so the question now arises, how best to do that? Well, if you look down your table, an exponential times a function of s. An exponential times a function of s. Okay, second shifting theorem. Second shifting theorem is what you would want to apply here. So with the second shifting theorem, this is really what's driving it. You want to take the inverse transform of this and then shift it and then multiply through by a suitable step function, heaviside step function. Oh, I've missed out a term, haven't I? Yes, sorry, I've missed out a term here. 1 minus this. Okay, thank you. So okay, so you've got a common factor of s squared. Make sure your form's in this. Okay, so if I let's just write out one more term. Okay. So now we want to take the inverse transform of these, the second shifting theorem in the second term, and how do I calculate the inverse transform of this? Well, these two things, the inverse transform of these two things are the bits that are driving the rest of the solution, okay? So if I can, let's just see if I can compute the inverse transform of 1 on s squared bracket s squared plus 4, and then I can apply it to both parts of these bottom line using the second shifting theorem in the second case, okay? Okay, well, how can I simplify this? Partial fractions, you might think. And that's, you can do that if you want to. Is it necessary? No, it's not. But the question here is, how do I, say, play with the numerator to get it something like s squared or something like s squared plus 4? If we had a 4 here to start with, instead of a 1, can anyone suggest something? Yeah, add s squared and take s squared away. But we don't have a 4. But can I make it a 4? Yes, I can. I can multiply by 4 and divide by 4. Okay? Okay, so what I'm going to do is multiply by 4, divide by 4, add s squared and take s squared away. Now if I just bracket it like the following, look what happens. If I split it up into two terms, how good is that? Huh? Huh? Not bad, huh? But if you want to do it by partial fractions, feel free. Feel free. Okay, so we want to take the inverse transform of these. Well, I can find the first one there, and the second one is going to be something like sine. Okay? So now I have it as a suitable form. Okay, so to take the inverse transform there, that's no worries. Here I want to use the second shifting theorem. So let's just call this, I don't know, g of s or something. Okay. Okay, so I can find both of these in the table. The first one's going to be t, and the second one's going to be something like a half sine 2t from a table. And so all I want to do now is I can take the inverse transform of that, and I want to take the inverse transform of that using the second shifting theorem. Okay, so I've actually got that term right there. And to get this, I just take this, shift it, and multiply through by a Heaviside step function using the second shifting theorem. Okay, so it's this function just shifted and multiplied through by this particular step function. Okay, so take this and just replace t with t minus pi on 2 in brackets. Phew.